Consider this body subjected to applied loads, and the body is restrained at certain locations. So these externally applied loads give rise to internal stresses in the body, and if we cut out an element from the body here, we expose the stresses acting on the element. So one of these stresses is the axial stress in the horizontal direction. So the first subscript that we use represents the normal of the face that this stress is acting on, and the second subscript represents the direction. So this stress acts in the horizontal direction. And similarly, this stress acts on the face with the normal pointing in the y direction, and the stress itself acts in the y direction. And we have another axial stress on the face with the normal pointing in the z direction, and that stress acts in the z direction. So remember that stress is force per unit area. Now if we denote the finite lengths of this element as delta x, delta y in the vertical direction, and delta z in the z direction, then we can observe that the axial stress in the horizontal direction stretches the element in the horizontal direction by some distance delta u. So therefore the strain due to this axial stress in the limit is the change in u with respect to the undeformed length of the element. So in the limit we have the partial derivative. And similarly, the strain due to the vertical stress acting on the element is the change in v with respect to y. So we denote the displacement in the vertical direction as v. And similarly, the axial strain in the z direction is the change in w with respect to z. So w is a displacement in the z direction. Now in addition to the axial stresses, which are perpendicular to the faces that they act on, we have the shear stresses. So this shear stress in the vertical direction we denote tau, and it acts on the face with the normal in the x direction, and the stress acts in the y direction. So it's tangent to the surface. So this complementary shear stress acting on the face with the normal in the y direction acts in the x direction. So these shear stresses give rise to shear strains. So this couple over here is going to distort this undeformed element as follows. So that gives rise to the shear strain in the xy plane, and the other two shear stresses distort the element as follows. So this here is the strain due to the shear stress yx. So the shear stresses effectively act to distort the element. So therefore epsilon xy is the change in the displacement v in the vertical direction as we move along the x direction. And epsilon yx is the change in u, which is a horizontal displacement, as we move along the y direction. And for a section that's not rotating, so it's undergoing pure shear deformation, these strains are equal. And then we can define the shear strain as that 90-degree angle minus this angle theta. So effectively the total shear strain in the xy plane is the sum of these two strains. So du dy plus dv dx. And similarly, we have the other shear stresses. So this is the shear stress acting on the face with the normal in the y direction, and it acts in the z direction. And we have another shear stress here that's acting on the face with the normal in the z direction, and it acts in the y direction. So that is these shear stresses over here. So that's tau zy, and then on the top face we have the complementary shear stress tau yz. So these cause distortions in the yz plane. So this shear stress couple is going to cause the following distortion, which is the shear strain epsilon zy, and then this shear stress couple is going to cause the following distortion in the yz plane. So this is epsilon yz. So pause the video and try to write these strains as we did for the xy plane while we continue. So the shear strain yz is the change in a displacement in the z direction as we move along the y direction. And epsilon zy is the partial derivative of v, being the vertical displacement, as we move along the z direction. So therefore the shear strain in the yz plane is the sum of these two strains. And finally, we have the other shear stresses, being tau acting on the face with the normal in the x direction and pointing in the z direction. And here we have the shear stress acting on the z face and pointing in the x direction. So this couple over here causes a distortion in the xz plane that looks something like this. There'll be epsilon xz. And then this other couple in the front and back face causes a shear distortion that looks like this. So there'll be epsilon zx. So similarly, we can write the strains epsilon xz as the change in w as we move along x, and epsilon zx is the change in u as we move along the z direction. So therefore the shear strain in the xz plane can be written as du dz plus dw dx. So given that these subscripts describe two directions, strain is a tensor quantity, and so is stress. So we can write them conveniently in matrix form. So on the diagonal, we have the axial stresses, and in the first row, we have the shear stresses acting on the face with the normal in the x direction. And in the second row, we have the shear stress on the face with the normal in the y direction. And finally, we have the shear stresses acting on the face with the normal in the z direction. And the strain tensor can be written in a similar way. So corresponding to the axial stresses, we have the axial strains on the diagonals. And corresponding to the shear stresses, we have the shear strains. And I'll just remove this arrow to make space. And note that the complementary shear stresses and shear strains will be equal to each other for a body that's not subjected to couples. So for example, tau xy is equal to tau yx.